Some of you are logging on just now, so I'm waiting just for a moment. Good morning. This is Bill Karwin from Percona Incorporated. This is Models for Hierarchical Data with SQL and PHP. Just to introduce myself, I'm a consultant at Percona Incorporated for MySQL performance and data modeling and best practices. My background, and I've been doing that for about 20 years in a variety of languages, but mostly in SQL. I've been focusing on that for about 15 years. I've also written a book called SQL Antipatterns, Avoiding the Pitfalls of Database Programming. That came out last year. Okay, enough about me. You probably want to hear about hierarchical data models. This is a problem that we've probably all faced with developing applications and managing databases in MySQL or any other database, and that is to store hierarchical data, tree-like data, and query it back efficiently. And examples of that could be if you've got a product catalog and you have categories and subcategories and sub-subcategories of items in your product catalog, you want to make sure to be able to manage those effectively. Bill of materials or parts assembly problems where parts can be composed of subparts, and then you want to collect them, for instance, and say, what is the total cost of this car engine with all the parts that are comprised by it? Another example would be threaded discussions. If you've got a forum online and you have people replying to each other, a reply is a form of a child record of the comment that it replied to. Or it could be any of those types of interactions where there are heads and hierarchies going on. Okay, so those are just examples. Let's see a more concrete example. If you've got a bug report database, for example, and you have people commenting on the status of a bug, Fran says, what's the cause of this bug? And there's two different threads of discussion from that. I think it's a null pointer. No, I check for that. The other thread says, we need to check valid input. Yes, that's a bug. And so on. You can see the example on my slide. So we're going to cover solutions to this, different ways that people store that type of data in hierarchies in a database. I'm going to cover 4 solutions: adjacency list, path enumeration, nested sets, and closure table. First up, adjacency list. This is the solution that you see most often in textbooks, and you've probably all used it. It's very simple. You add a column in each row of your hierarchical data that denotes the ID of the parent of the current row. So in the case of the threaded discussion that I just showed, you could see that the parent ID is the one to which the comment was replying. It's very simple. Adding a new row to this is also very simple. If you want to add a new comment as the reply to comment number 5 in this case, Ollie says, yes, that's a bug. And Fran says, I agree. All you do is add a new row that denotes the parent as being comment number 5. It's also easy to move a node or a subtree. You just change the parent. So if we want to move comment 6, yes, please add a check, over to the other side of the tree, we change that value and just replace it. Any other further child nodes of the subtree are automatically updated. They actually don't need to even know that they changed the position in the tree. It's also simple to query immediate child and parent. But the problem with this design that we all run into eventually is that it can't handle deep trees. If you've got a tree that can go to unlimited depth and you need to fetch all the rows back, you can try a technique like this, but that's still only going to you'd have to write an infinite number of left joins in order to go all the way down to an arbitrary depth tree. In SQL 99, syntax was introduced to handle recursive common table expressions that account for this. And this is a solution that works well with the adjacency list database design. Other databases support this, but MySQL and a few others don't support this yet. So what do we do? If you're using MySQL, there's a few other solutions that you can use. The first I'll cover briefly is path enumeration. In path enumeration, you could store a varchar or a string, I'm calling it path in this example, that is simply a concatenation of the chain of ancestors, the parents, the grandparents, and all the way back up to the root of the tree, and with some delimiter in between them. This is the same kind of thing as a directory path in a POSIX shell. You'd see your parent directory and the grandparent to the left and on the way up to the root directory. I'm seeing a comment that the slides aren't moving effectively. I'll try to go as path enumeration is good if you typically do queries for breadcrumbs. You already have the list of breadcrumbs all the way up to the root of the tree already stored in your row, and you can get that easily. If you're using path enumeration, you can query for the ancestors of a given comment or the descendants of a given comment using SQL queries like these, where you do string matching using the like predicate, and that works out fairly well. And then you can also add a new child just by adding a row to your table of comments, copying the string of ancestors from the parent that you're making this as a new child of, and adding the new insert ID that you just inserted. That's all I'm going to say about path enumeration for now. I don't actually see this used very commonly among developers creating applications with hierarchical data sets. Let's talk about the other designs. Nested sets. There's a famous article that is popular on the MySQL website that covers this. They also modified and it was popularized by Joe Selko in his books of SQL for Smarties. The idea is in nested sets is that each comment has two numbers associated with it, and the numbers are chosen so that the left number is less than all numbers used by the comment's descendants. The right number is greater than all numbers used by the comment's descendants. It's easier to show you this than to describe it in text. So if we have our tree, we can enumerate these and assign two numbers to each of the nodes in the tree. And you can see that for each node, the numbers that it has are less than and greater than all the nodes beneath it. You can also, if you trace them in numerical order, you can see that you're doing a depth-first traversal of the tree. Down the left side, and then up, and on the right-hand side, all the way back up to the top of the root node. So in your tree structure, you would store these as two extra columns that denote the left and right number for each node. Note these are not foreign keys, they're just integers that are associated with the node, and they allow you to describe the tree. So how do you use this? If you were to need to get the ancestors of that bottom node in the tree, number 7, I'm getting a comment that the slides are still acting funny. I apologize for that. I'm not sure what I can do about that. I am sharing this application, or this slideshow, as a PDF. Nikki, do you have any comments on how to make the slides move better? But I'll keep going if there's nothing else. No, I'm sorry, this hasn't happened before. So I will keep going as best I can, and we can hope to move on. And I will be sharing these slides online. The only other thing I can try is to share my desktop and run the slides that way, but I'm not sure that that would be any better. Are we caught up now to query ancestors of number 7? Thank you. This slide is showing if we are looking for the ancestors of the very bottom node, the number 7 saying Kukla, that fixed it. The ancestors are all those nodes who have numbers on either side of the numbers associated with that bottom node. So 9 and 12 are numbers that are outside the range of 10 and 11, which are associated with the bottom node, and likewise all the way up the chain. The other numbers are not don't fit that pattern. They aren't. They don't have numbers that 10 and 11 are between. Likewise, query ancestors. Excuse me. Needed to advance the slide a bit there. The other way is to query descendants, a subtree under a given node. If we want to check node number 4, Kukla, we need to check valid input and get the ones that are below it. It's simply the nodes that have numbers that are between the numbers used by the root of that subtree that we're looking for. And this is what that SQL looks like. So fairly simple SQL. It can be tricky to insert a new child node into the tree. If you need to add a new child of node number 5, all he says, yes, that's a bug, and we want to have Kukla agree. First, we need to make space for that. We need to advance all of the numbers to the right and above to make a couple more numbers available, and then we can insert that new node. So this gets a little bit more tricky. You can use this update statement, shift over just the numbers that you need to, and then insert the new comment that has the new numbers 8 and 9 associated with it. What's even more tricky is to query the immediate parent. We don't want to see all the ancestors. We just want to know the immediate parent of a given node. So number 6 says, Fran, yes, please add a check. We want to get back just the immediate parent. Number 4, Kukla, we need to check valid input. And unfortunately, this is what that SQL looks like. So the parent of number 6 is the ancestor who has no descendant who is also an ancestor of number 6, which is a little bit twisty in a way of thinking of it, but it does work. And the reverse, querying an immediate child of a parent node is a similar problem. It has a very similar structure to the SQL. So that's a bit harder and less straightforward. Let's take a look at another solution that I've used before. And I call this closure table. I don't see people talk about this too much in books and magazines or blogs, but it's worked out well for me in projects in the past. In this design, we create a second table. In addition to our table of comments, we have this other table which looks a bit like a many-to-many table. In this one, we note every ancestor and every descendant. So we're going to store many paths through the table. In fact, every path from each node to each of its descendants. And a node even connects to itself. That is, a node is its own ancestor and its own descendant. Let me show that graphically. if we start out with our tree that we used before, we have all the paths that go from the root node down to all of its descendants, as well as all the intermediate paths of nodes in the middle of the tree to their descendants. And finally, all of the nodes point to themselves. I call these reflexive paths. I'm going a little bit slower on the slide advancement so that hopefully it'll catch up for everybody. What does this look like in tabular form? Well, the comments table that we had doesn't have any extra columns as it does in the other designs we looked at. Instead, we have a second table that just stores the ancestors and descendants and has pairs of numbers, which are foreign keys, back to the comments table. In theory, this requires up to order n squared rows, but in practice, you would get far fewer. If you had a very, very shallow tree, you would have very few. And if you had a very skinny tree that goes deep, you would have 2 times the depth. But most trees are somewhere in the middle. They have a number of children at each level, and they have a number of levels that they go deep. So let's see some queries of using this. If we want to see the descendants of node number 4, we can just query from all of the paths whose ancestor is 4. Let me show you that graphically. That is, starting at node number 4, Kukla, we need to check valid input. And we see all of the, I'm getting a comment that slides are moving better for me now. Great, I'm glad. So we see all the paths that are starting at number 4, that is the path whose ancestor is noted as number 4, and that points to all of the immediate children and grandchildren and on down the tree, including number 4 itself. That's where the reflexive path comes in handy, because typically when we want to query a subtree, we want to include the node that's at the root of that tree too. The reverse operation, querying ancestors, is also a fairly simple SQL statement. And here's what that looks like. If we start at that node number 6, Fran says, yes, please add a check. And we want to see all of the ancestors back up to the root of the tree. We need to get nodes where there is a path that terminates at the descendant of number 6. That is, any path that starts anywhere up the tree and finishes at number 6. That also includes the reflexive path for number 6 because it's its own descendant. And that's typically what we would want. If we want to start at number 6 and get the breadcrumbs back up the tree, we want to also include number 6 in that result. Here's another operation that we would typically do on a tree, inserting a new child. And we'd use the same example that we did earlier. Fran says, yes, I agree. And she wants to insert into the tree paths, copying the paths that terminate at the parent that she wants to add her comment to, and then also a union with a new row, which is her own reflexive path. So notice that it's copying all the paths from the parent that she's attaching to, which is node number 5, but changing the descendant to 8. Let's show you that graphically. So the bright blue node is the new one. It's being created as a child of number 5, which already has paths pointing to it. So we copied those paths, but changed the descendant in our copy to point to the new node. That's also where the reflexive path comes in handy, because we've just copied it but changed its descendant destination. And then we add one more for the reflexive path for 8. Deleting a child. If we want to delete a child, all we do is delete paths that terminate in that child. So 7, the one at the very bottom of the tree, We just take away the paths that point to it and then freely remove the comment itself. That's where it used to be. If we need to delete a whole subtree, we want to select for all the paths that start from the root of that subtree and then delete all the paths that terminate in any of those descendants. So here's the way that looks graphically. If we want to delete the subtree starting at node number 4 and all the nodes beneath it, we remove all the paths that terminate in any of those descendants. And then we can remove the nodes themselves. There's one other variation of this design that is very useful. Getting a client with somebody that always static key. I apologize for that. I'm going to go on just a moment to hold that clears up. Okay, I'm back. Is the audio any better? Okay, I'm back. I'm going to try this again. Hopefully Skype is doing better. Okay. Sometimes Skype just needs a breather, and so do I. Okay, going back to the slide, I'm talking about path length. We add another third column to my tree paths table that denotes the length of the path that's being encoded. And that is 0 for the reflexive paths, 1 for immediate parent-child relationships, and a greater number when we're talking about a longer path. So then we can have a very easy way, as shown by the SQL query here, that allows us to see immediate children of a given node. The operation that was so easy with Adjacency List is now easy again. So summarizing the different table designs, each of them has different strengths and weaknesses, different operations for which it's hard or easy to do queries. And there's also a final column in this comparison, which is whether the design supports referential integrity. That is, in Adjacency List and Closure Table, we get real foreign keys, whereas in the other designs, path enumeration and nested sets, there's no referential integrity there. You're sort of on your own. Okay, so in order to demonstrate the closure table design, I developed a PHP application. I'm going to hope to share that. We'll see if my sharing desktop works okay with this presentation. I want to talk about it for a few slides first. For test data, I've used some data from the Integrated Taxonomic Information System. This was a great source of data because there's over 500,000 scientific names for plants, animals, fungi, and microbes. And they are in a free data set that's organized into a hierarchy. So it was a good bit of test data to use for hierarchical testing. So, for example, the California poppy. This is my state flower, and its species is Escultia californica. So it is in a hierarchy that goes several levels back up to the top of the taxonomic system. As the data I got from ITIS shows, they use a path enumeration. They have a varchar that is the chain of ID values all the way up to the top of the tree. So I converted that to my closure table design. And I created some PHP classes with functions to query by whole tree by root, or fetch a set of breadcrumbs, that is the chain of ancestors back up to the top of the tree. And then some container classes to hold a row and a row set. These are, you may be familiar if you're a PHP programmer, these are extensions of the Zen framework database abstract layer, which I worked on for a while when I was doing PHP programming. Here's how one would use it. I just create a concrete table, ITIS table, extending my abstract table that holds the queries that I would do against the closure table, and have some protected values that name the SQL tables that contain the names, and then also the closure table, the tree paths table. Once I have my table object, I can simply fetch breadcrumbs and give it the ID value of the California poppy, and that hands me back an array, which I can then output with a separator of a arrow greater than symbol. Here's what the SQL would look like. We saw a similar query to this earlier. This is simply the list of ancestors of a given node. And I'm ordering by the length of the path. So it naturally gives the longest one first. So it'll show the, or it gives the longest one first since I'm doing descending. So it shows me the nodes in order from the root down to the leaf. Okay, biggest question is, how does it perform? Given that I have 500,000 nodes in my tree, and goodness only knows how many paths, you would think that this would take a long time to get through. But with the proper indexes, it takes less than 1,000th of a second. The next thing I wanted to be able to do is dump out a whole tree. Starting from the root, I wanted to get, or a root of a subtree. The whole tree would be 500,000 nodes. I just want a few dozen nodes. So I'm going to start from a node that's just a couple levels up from my California poppy flower and dump out the tree from that. And this is what it looks like. There's a few more items that didn't fit on this slide. Here's what the dump tree SQL looks like. And I noticed that I have this other term in there, so I'm going to be expanding each level of the specific nodes as I drill down into the tree. How does this perform? Well, this took 0.2 of a second to show that tree, and that's just running on my MacBook Pro. Presumably, you would be running this on a real server, and it would be running a lot faster. But again, it's making use of index as well. Here's the indexes that I actually created for it. You can see that I created indexes on several combinations of different columns to support different types of queries. And that's how it can do index-only queries. And you may also be interested in how many paths it ended up creating for this collection of nodes. Well, it created about 4.6 million rows, which isn't really all that bad for 500,000 species. And you also see that I have almost as much index storage as I do data storage. Okay, now let's see if we can do a demo. I'm going to switch over to sharing my desktop. All right, so here my browser with my closure table demo with ITIS data. You can see that I have first shown the breadcrumbs for the Escoltia californica, and that's the query that only took less than 1,000th of a second to render. And then I have the first level deep of plants at the bottom. And I have used CSS for this demo just to highlight in green the items that I need to click on. So I'm going to click on these and tell you when I click so you can see how rapidly it renders. And if WebEx is responsive, you can see that it comes up. So here we go. Click. 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 Click, click, and there it is, Escoltia californica. Now, I wasn't doing any variable, no caching, except for whatever the MySQL server does, checking the indexes in the InnoDB buffer pool. And memcached, no, nothing like that. This is doing live queries against the data that comes back in a second. So that's fairly good. And let's go back to my document. Alrighty. I talked about this design a little bit in my book, SQL Antipatterns. You can see the URL for it there, as well as many other solutions for other types of SQL problems. I also wanted to mention that Percona is going to be at the MySQL User Conference in April. So please come by and join us, see what's up at the MySQL User Conference. And if you want to go and you haven't registered yet, there's a discount code that you can use for registering at 20% off. Okay, so now that we talked about different solutions for hierarchical data models, I'd be glad to take any comments or questions that you want to share. All right, we have a question. You can feel free to type it into the comments window, and I'll do my best to answer it. Thanks for the good presentation. Thank you for attending. I'm glad to do it. I believe we do offer the presentations recorded and put that up on our website. And we'll be doing our best to make that happen promptly. Question is, how can we make the closure table maintained automatically? Well, as you insert your rows to the closure table, just as you would with any other table, you have to enter those values in. when you insert a new comment into the comments table, you won't necessarily know where that belongs in the tree. But putting it into the tree involves copying the paths from its parent, as I showed, putting it in there. What's nice is that when you want to delete a leaf node, you can just use cascading foreign keys to automatically delete that and all the paths associated with it. Next question. How easy would it be to remove a node but preserve the child nodes using closure model? So I assume you mean remove a node from the middle, but it has further child nodes that you want to then be promoted. Well, you would first move those nodes to be the children of the parent of the one you're removing. And I actually wrote a blog on moving subtrees or moving individual nodes. And that's on mysqlperformanceblog.com. And I just wrote that in the last couple of weeks. And it shows some examples of how to move child nodes or child subtrees around in the tree. Janice asks, could we use a trigger to maintain a tree automatically? Perhaps, but I would be concerned about creating chains of nested triggers that would go too deep if your tree is very deep. So I would prefer to do it with SQL statements directly. And you can remember with an SQL statement, you can update or delete or insert copies of a whole collection of paths. So those could be done very efficiently. With triggers, I would be afraid that you would have to execute a trigger for each path in the tree, and that would create a lot of executions. And each of those triggers would then execute one or more SQL statements, and it would be a lot less efficient than doing a set-oriented query that affects all the paths at once. George asks, which is the most scalable solution of the four that I presented? Well, each solution has its own strengths and weaknesses, and you have to figure out in your application which are the operations that you need to be the most scalable. For example, Adjacency List is great if all you need to get are immediate child or immediate parent. You don't need to do any joins. You just have the information right there in the row that you're looking at. But it's less scalable, Adjacency List is, if you need to query for whole subtrees. So it depends in your application which are the operations that you need to be scalable. And that's got to be the answer. There is no single answer about which is most scalable. Okay, any other questions? Great, thank you very much for attending, everyone. I really look forward to doing more presentations in the future for Percona.